Alright, we have already seen what is a physical representation of the stress tensor and also how we write that mathematically as a matrix. The stress tensor has 6 independent components, and in general, unless the principal stresses are aligned with the coordinate system which is written, these diagonal and off-diagonal values are going to be non-zero values. However, we can always calculate the principal stresses and the principal directions for such a stress tensor, and it will be always possible to find these principal stresses and principal directions, for which we can write the stress tensor just with the principal stresses, and these stresses are going to be normal to the faces of the cube. Let's say sigma 1, sigma 2, and sigma 3. Notice that all the principal stresses are aligned with the principal direction that it corresponds to. Likewise, we can write this mathematically as a matrix where we have now sigma 1, sigma 2, and sigma 3, and all the off-diagonal terms now are going to be equal to 0. These two stress tensors are equivalent, but are written in two different coordinate systems. Okay, so in this case, in the first case, we have 6 independent components, and here also we have 6 independent unknowns, to put it in one way, 3 principal stresses and 3 directions that we have to determine. And you could imagine that plotting, for example, a stress tensor in a 2D space or in a 3D space is quite difficult, because you have to plot 6 independent values on top of each other, and that's quite difficult, if not impossible, at least in our universe. So instead of that, what we're going to do is we're going to simplify the stress tensor so we can capture some values that we're interested in. For example, instead of plotting the entire stress tensor, you could plot the minimum principal stress, sigma 3. If you do that, for example, in a 2D or in a 3-dimensional space, you could find out which are the points in a solid which are subjected, let's say, to tension, or which are the points that are subjected to a value lower than a tensile strength value. You could do that. And here we're going to see several ways that we can plot the stress tensor in a way that it's easier to understand, at least easier than just looking at the numbers only. Okay, so the first thing that we're going to do is we're going to see what is the 3D Mohr Circle. And the 3D Mohr Circle is actually pretty easy. In a 3D Mohr Circle, what we do is we plot in the x-axis the effective normal stress, and in the y-axis we plot the shear stress tau. This effective normal stress and shear stress correspond to the stress on a given plane of at a particular point. So if I take the cube that I had on top with the principal stresses, then I could slice it with a plane that, for example, cuts through here. And now if I remove this top part, I'm going to be left with just the lower part, and if I had applied here sigma 2, sigma 1, and sigma 3, then the stress I will need to apply on this plane, because I removed the previous one in which I already had stresses, these stresses are going to be normal to that plane, sigma n, and on the plane itself, the shear stress tau. So I could slice this cube with any three-dimensional plane, and the result is going to be that in order to keep it into equilibrium, I need an effective normal stress and a shear stress, which are going to be sigma n and tau. And these are the x-axis and the y-axis for the Mohr circle. So the 3D Mohr circle then is going to be composed by the three principal stresses. Let's say sigma 1 over here, sigma 2, and sigma 3. In order to draw this Mohr circle, the only thing that we have to do is to join these points or these principal stresses with circles, and the result is going to be a area bound by these three circles. This area which here I am filling with crosses, it's the area of all the possible state of stresses, including the circles themselves, that are applied on the cube that I have on the right. At any of these points, I'm going to have a combination of effective normal stress and shear stress. How to calculate that point is something that we're going to see later on. But what I like to highlight from this plot is that the Mohr circle shows graphically the stress tensor, and the bigger the diameter of the circle, the larger the shear in the stress tensor. You could also look at the diameter of the circle just by looking at the difference between the principal stresses. And the larger the difference between the maximum principal stress and the minimum principal stress, the more shear you're going to have in such a solid. There could also be shear with the other principal stress, and that's going to be characterized by the intermediate principal stress. But if you want to draw a Mohr circle, a 3D Mohr circle, the only thing you have to do, again, is just to find out what the principal stresses are, sigma 1, sigma 2, sigma 3, plot those in the x-axis, join the principal stresses with circles, and the area bound by those three circles is going to be all the possible state of stresses that could happen in this point with these stresses. Notice that this 3D Mohr circle applies just to one state of stress. So still, I have many possible values that could be a combination of the state of stress and the intersection with this plane. All right, but this serves as a good motivation about how to simplify a little bit more the stress tensor in order to plot it and to use some other values that we're going to see are very useful. So motivated by the Mohr circle, let's try to separate the Mohr circle in two parts. Let's just look at one Mohr circle, and let's say that I have a Mohr circle for which This is sigma 1, this is sigma 2. The center of the circle is right here, and the radius of the circle is this. I could break this Mohr circle in two parts. And these two parts are going to be the first one, which that just depends on the center of the circle, the center C, and it's just going to be a point in the x-axis with coordinate in x sigma 1 plus sigma 2 divided by 2. It's just the center. And to that, in order to hold this equality, I would have to add the other part that depends on the radius. And that's going to be a circle which it has a center at the origin and has its principal values at coordinates in x sigma 1 minus sigma 2 divided by 2 and negative sigma 1 minus sigma 2 divided by 2. So the first component is what is called the isotropic component of the stress tensor, and it's called isotropic because it means that the stresses in all directions are the same. When a Mohr circle has a radius equal to 0, that means that all the stresses in all directions are the same. And the second part, it is what is called the deviatoric part. And this deviatoric part consists in pure shear. As you can see, the mean stress in such stress tensor is equal to 0. It's just got shear in it. And by doing this decomposition of the stress tensor, we can recognize what is the part that composes the mean stress and what is the part that composes the shear. This is very important because, for example, in a rock, we know that the higher the compression or the mean stress, the mean compressive stress, the stronger the rock is going to be. So the further to the right I have this point, then the stronger that rock is going to be. We also know that all materials can fail in shear, and the bigger the radius of the Mohr circle, the closer I might be to shearing. So the size of this circle or the diameter of the circle is very important in order to know if I might get to shear failure or not. Okay, this graphical decomposition is valid for just one Mohr circle, and we could say for 2 dimensions. Let's see how this will work in the case of a 3-dimensional stress tensor. And we're not going to do the graphical part because that's going to be a lot of circles. Instead, let's just do the algebraic part, and just with the matrix. So any tensor can be also decomposed into an isotropic and a deviatoric component. And this is going to be very similar to what I have before. Let me just line up this with a plot on top. The matrix is going to be composed the isotropic matrix by the mean stress in the diagonal and zeros in the off-diagonal terms. Here, the mean stress is equal to the average of all the normal stresses. This is a quantity that we're going to see is going to be always the same no matter in which coordinate system you write your stress tensor. And the deviatoric part is going to be what I'm writing right now. As I write it, you may want to double check that when you add up these two stress tensors, the result is what we have on the left of the equal sign. Okay, last row. Okay, and this is going to be the deviatoric tensor. Let me write here. This is the isotropic component. This one is the deviatoric component. And it's the same thing as what we had before. And I can also simplify this to having just a stress tensor written as one variable. This is going to be equal to the mean stress times the identity matrix in 3 dimensions plus the deviatoric stress tensor that usually goes with the letter S, and S comes from shear. Okay. So now that we have these two stress tensors, let's go a little bit further into trying to obtain just one value which is going to characterize the isotropic stress tensor and one value that is going to characterize a deviatoric stress tensor. In graphical terms, what we're looking for is in the isotropic component is just the location of this point, how much compression or mean compression that we have, and in graphical terms, for the deviatoric stress tensor, we're looking for how much shear we have in this particular solid. And in order to do that, what we're going to use is the definition of invariants. And the definition of the invariants, we have 3 invariants for any stress tensor. They are called invariants because they do not change with respect to the coordinate system, and no matter which coordinate system that we use, these values are going to be always the same. And let's go and start with the first invariant. Invariant number 1 of the stress tensor is equal to the summation of the terms in the diagonal. And as I was telling you just a second ago, this value is not going to change no matter what coordinate system you use. So for example, if we were to use the coordinate system of the principal directions, this is just going to be the summation of the principal stresses. And if we want to use the first invariant in order to define the mean stress that we have over there before, mean stress is going to be equal to the first invariant of the stress tensor divided by 3. There are 2 other invariants. The first one is the most useful one, and we're going to have the second invariant and the third invariant. The second invariant is going to be calculated with the equation I'm writing right now, and it's a summation of products of the principal of the stresses in the diagonal with also a quantification of the off-diagonal terms. And the third invariant is going to be equal to the determinant of the stress tensor. And if you use the principal stress or the principal stress tensor in order to calculate the third invariant, this is just going to be the product of the principal stresses because the off-diagonal terms are going to be equal to 0. But from here, the more important or the most used invariant that we're going to use is the first invariant. And notice that now we just reduce the isotropic tensor to just one value. Sometimes we use the entire invariant, invariant number 1, or some other times we just use mean stress, which is a little bit more handy to use. These are the invariants of the stress tensor. We can also calculate the first, second, and third invariant of the deviatoric stress tensor of just this component over here. And in that case, it's the same equation, but we call it by convention J. So the first invariant of the deviatoric stress tensor, ST, is going to be equal to the summation of the diagonal terms in the matrix. But if we look at the matrix, you can see that if we add sigma 1, sigma 2, 2, and sigma 3, 3, that's going to be equal to 3 times sigma m, and 3 times sigma n minus 3 sigma m is going to be 0. So the first invariant of the deviatoric stress tensor is going to be equal to 0. The second invariant of the deviatoric stress tensor is going to be the one that we're going to use more. And notice that the second invariant characterizes the terms with shear, or is proportional with to the off-diagonal terms. If we calculate the second invariant of the deviatoric stress tensor following this equation over here, you will find out that you can reduce this in terms of the principal stresses to the equation that I'm going to write right now. And notice that here, the second invariant is quantifying the difference between principal stresses. And from the graphical representation of the Mohr circle, we know that the difference between principal stresses is equivalent to a diameter of a Mohr circle. And the larger the diameter of the Mohr circle, the larger the shear. And this is going to be the second invariant of the deviatoric stress tensor. And that's something that we're going to use as well because it characterizes shear. The third invariant of the deviatoric stress tensor is, as we were saying, if we write this in terms of the principal stress coordinate system, the product of the elements in the diagonal. Later on, we're going to see that we'll also use the third invariant of the stress tensor. But for now, let's just leave it to I1 and J2. All right. How can we use now I1 and J2? Well, what I have done is just to quantify in a three-dimensional coordinate system and a stress tensor, and I can quantify how much mean stress I have and how much shear I have. Instead of plotting 6 independent values of a stress tensor, I just have reduced the stress tensor to 2 meaningful quantities. And this is very useful because I can now plot, for example, the evolution of stress with time. This is what is usually known as a stress path. For example, I could plot in the x-axis the invariant number 1. That tells me how much compression I have, especially if we are working in geomechanics where compressive stresses are prevalent. And J2 is characterizing how much shear I have. Let's say, for example, that in a particular location around the wellbore or in a reservoir, my initial state of stress is somewhere over here. Let's also say that I have gone to the laboratory and I have find out that the yield stress of my material is characterized by this equation, where J2 is equal to the combination of a constant and the invariant number 1 multiplied by another constant. And this characterizes how much shear I can have for a given mean stress. Usually rocks have the property that the higher the compressive stress, the more shear they can bear. And this is what this equation is capturing. All right, so I could change the conditions of this particular state of stress. And let's say this is at time 0. If I change the conditions so that I make this solid to get increased compression and increased shear, then I could plot this like that, where as time passes by, I know in which direction the solid is moving. And this is what is called a stress path. And it allows me to see how stresses are changing in time in a simplified version by just looking at the shear and the compression in it, two numbers that characterize those two. Let me also add here probably a more familiar plot for all of you. What I have just drawn is equivalent to drawing more circles. But with more circles, we have to draw 3 circles. So that's why it's a little bit more complicated. But let's say that my initial state of stress is somewhere around here, and I have a 3-dimensional state of stress. So I'm going to draw 3 circles. And the shear yield for this particular rock is somewhere over here, where the maximum shear stress depends on the cohesive strength of the rock plus effective normal stress times the tangent of the friction coefficient. The plot on the right is almost exactly the same as the plot on the left. But on the plot on the left, I have reduced 3 circles and 3 principal stresses to just 1 point. But it is exactly the same thing. If I wanted to plot this as a function of time, then this Mohr circle on all of them will move in the direction in which is shown in the arrow. But it's exactly the same. Okay, now that we have seen the application of these invariants, let's see the definition of 2 other invariants that we're going to use as well, and that you may also find in papers that you read. So for soft sediments, there are two other definitions that are very useful. This comes from the theory of soil mechanics, and it applies very well to many unconsolidated sands and shales, which exhibit large deformations and are relatively soft. And in this case, the most popular definition or characteristic values for the stress tensor are P prime, which in this case is just equal to the mean stress, and remember that this one is effective stress. This is very important. You're going to find also in several books that effective stress is usually denoted with this prime. And here we're just going to use sigma to denote effective stress. And we also know that this is just the first invariant of the full stress tensor divided by 3. And the other value is Q, where Q is defined as the square root of 3 times J2. Notice that J2, if we look at the equation again, has the units of stress squared. So if we want to get that in units of just stress, we need to take the square root of that. And particularly for conditions in which the two of the principal stresses are equal, and that is found usually in what are called axisymmetric conditions, we'll see that P and Q take simpler definitions in the values. So let's say that I have now an axisymmetric or cylindrical solid subjected to this state of stress where sigma 2 is equal to sigma 3. In this case, P is going to be equal to sigma 1 plus sigma 2 plus sigma 3 divided by 3. But since sigma 1 and sigma 3 are, since sigma 2 and sigma 3 are the same, I just can write this equation as sigma 1 plus 2 sigma 3 divided by 3. Also, let's see what will be the case for Q. Q is going to be equal to square root of 3 times J2, and the definition of J2 is 1/6 of the summation of the squares of the difference in principal stresses. So we know that sigma 1 and sigma 3 are different, and we know that sigma 1 also and sigma 2 are different. But since sigma 2 is equal to sigma 3, let me just write sigma 3 over here. And since sigma 2 and sigma 3 are the same, the difference is just going to be equal to 0. And as a result, I'm going to have this as the product of 2 times sigma 1 minus sigma 3, all of that is squared. And when I do that, then that's going to be a 2, and the 2 is going to cancel out with this 6. I'm going to get here a 3, and 3 is going to cancel out with a 3, and this is just going to be 1, and the square root of this is just going to be equal to sigma 1 minus sigma 3. So this characteristic invariant Q then in axisymmetric conditions where sigma 2 is equal to sigma 3 is just the difference between the maximum and the minimum principal stress. Okay, similar to I1 and J2, these P and Q parameters are very useful because I can also draw this with P in the x-axis, Q in the y-axis. If I had an initial state of stress somewhere over here, let me move a little bit more to the top, somewhere over here, and I had a shear yield line over here, I'm going to see that with soft sediments also, I'm going to have another component over here, which is due to compression. Excessive compressive stresses could cause a rock to yield or to achieve a plastic state in compression. And also, if I put too much tension in the rock, particularly in these soft rocks that have a low tensile strength, I might reach the limit for tension. And by characterizing the state of stress with just two coordinates, I can see very clearly, for example, if I go through a path of depletion, we're going to see later on why this stress path is moving towards compression. If we, for example, have this rock next to a wellbore and it fails in shear, we're going to see that the wellbore breakout stress path goes more or less in this direction. If we had injection of a fluid in a reservoir under 1D stress condition, 1D strain conditions, we're going to see that this is going to be the stress path. And also, if at a particular site on a tip, for example, of a hydraulic fracture, we could also see that the stress path is towards tension. So using these invariants, it's again, it's very useful for not only plotting the state of stress in a two-dimensional or in a three-dimensional state space, like for example using contour lines, but also for tracking the state of stress as a function of time. And this is something that we're going to do later on, but we see right now what is the use of these invariants. Okay, this is everything for this lecture. Let me just complete this sentence, and let me also use one more minute to show the application, or to add just a simple diagram of what we're interested in. So for example, if this is the sea floor and this is an offshore platform, we're interested in knowing what is the state of stress and what is the change of time in this particular site as we change, for example, pressure in this at this site. And for that, using these stress invariants is very useful. All right, so now this is everything for this lecture.